time is to conduct this test within this week. Anyway, I'll take coming Monday. No problem. You just tell everyone, okay?
Yes, sir. Thank you.
Inform this to everyone. So we are currently discussing, transfer function model. Previously, we have derived the transfer function for single input, single output or CISO system. We also developed the transfer function for multiple input, single output or MISO system. So today we want to discuss the development of transfer function and the corresponding block diagram for multi-input, multi-output or MIMO system. Okay. Now here multi-input, multi-output system, we are considering 2x2 system, which is basically the simplest MIMO system. Fine. But here I want to just mention that if it is more than one, then here we are considering multi. Okay, but in many chemical engineering text or subjects, if it is more than two, then only it is considered multi. I'm giving you one example, like if you consider a mixture having one component, it is single component mixture. If you consider a mixture having two components, it is called binary mixture. If you consider a mixture having more than two components, then only it is called multi-component mixture. Okay, but here if it is even two, we consider it as multi-variable system. This is a difference. Now, as I mentioned, this is the simplest MIMO system or multi-input, multi-output system. Schematically, it is shown here. You see, we have a process and we have two inputs, namely F1 and F2. And we have two outputs denoted by Y1 and Y2. Now for this MIMO system, we have this kind of model. Fine. Or if the model is not given in this way, we can restructure that model in this standard form. I repeat, this is the format for the model of a MIMO system. If for a particular example, we do not have this type of standard format, then we can reconstruct that model in this form. In fact, we will consider one example and see later. So this model I can represent in matrix form. This is the matrix form of a linear or linearized multi-input, multi-output model. As I told in the last class, you see the notation of this coefficient matrix A suffix 1 1. First suffix indicates the row and second one indicates the column. You remember this, it is quite common. First suffix indicates the row of this entry of a or element of a coefficient matrix, and second suffix indicates the column. It is true for this coefficient matrix as well. Now, since we need to construct the transfer function, that means we need to take the Laplace transform. Okay. Our transfer function model is in Laplace domain. Therefore, we need to convert this time domain to Laplace transfer model. Time domain model to Laplace transfer, Laplace transform model. So you see initial conditions are given here y10, y20. It indicates that the output variables are in terms of deviation variables. Okay, output, in fact, input variables are also given in terms of deviation variables. Now, as I told, we need to take the Laplace transform to represent the model in Laplace domain. Say, if you take the Laplace transform of these two model, and if you rearrange them or solve them for y1 and y2, we get this type of structure. I am directly giving you the equation, but the steps are like this. You need to take the Laplace transform of the given model and then solve them for y1 and y2 and get these two equations. Okay, I repeat, you take the Laplace transform for the given model, rearrange them to get y1 and y2, and these are the standard forms. I am directly giving here the equations for y1 and y2 in Laplace domain. You note down these two equations and you may verify whether these equations are correct or not later.
Sir, what is this PS?
Yeah, PS I am giving you. PS is this one. You verify these equations later. Now you see the nomenclature, particularly the suffix of this transfer function g. Can anyone tell how the suffix are given? I repeat the question. You see this is g suffix 1 1. This is g suffix 1 2. Here 2 1. Here 2 2. How they are denoted? Anyone can give the answer?
y1 f1.
Yes. So first one is what? First one is output or input?
Output.
Yeah, first one is output. So G suffix output and then input. You see the nomenclature is in that way given. G1 to here. First one is output, that means Y1. Second suffix 2 means input and that is F2. Similarly here you see GT1. First one is output, that means Y2. Second one is input, that means F1. So in this way the nomenclature for G is decided. Now let us write in this matrix form. Let us write them in matrix form. And when it is coming to the matrix, as I told, the notation is like first suffix indicates the row and second one is the column. Okay. Now in the next step, we'll go to develop this block diagram. You see, this is a block diagram. And to understand it, you just follow this nomenclature. First suffix indicates the output and second suffix indicates the input. So this y you write here y2. It is not y, it is actually y2. I did a mistake. I repeat, this second y is basically y2. Okay, and you can add here also plus plus, like here. Plus plus, they are getting added. So here plus, and this is y2. So do you understand the construction of this block diagram? Student, how this is constructed? Anyone can explain this? According to the given nomenclature. Yeah, Vardhan is there.
Yes, sir.
Can you explain?
I'm not sure of how to do this.
Yeah, you try at least. If not, I will definitely explain it.
Applying transfer functions on y1, f1, y2, f2, f1.
So it is somewhat like this. Suppose this is G11. So first suffix corresponds to the output y1 and second suffix corresponds to the input f1. So G11 should connect y1 and f1. It is like this. According to the nomenclature, first suffix indicates the output. That means y1. And second suffix indicates the input. That means f1. So f1 and y1 must be connected with G11 and it is there, you see. Now you come to the second one, G21. So first suffix indicates the output, that means y2. You see it is connected with y2. And second suffix indicates the input, that is f1. It is also connected with f1, you see. So like this way they are given. This block diagram is constructed. In case of G12, it must be connected with y1 and f2. You see it is connected with y1 and f2. Similar thing is applicable to G22. Now, another significance this block diagram has. As I mentioned previously, this f1 and f2, they are basically input variables. Okay, we also called before they are forcing functions. Fine. This f1 and f2 are input variables. Let us take one example. Suppose distillation column. So for the distillation column, what is f1 and what is f2? Anyone can tell me? For distillation column, what is F1 and what is F2? What are the input variables for a distillation column?
The input flow and Z.
Correct. What's your roll number?
19CH10037.
Yes. So you see, for the distillation column, F1 we can consider as feed flow rate F, and F2 we can consider as feed composition Z. Okay, there are many other variables also involved in the input section of a distillation, like feed pressure, feed temperature. Okay, those also we can consider. Now you see, if there is any change in, suppose F1 is capital F, that is feed flow rate. If there is any change in, okay, what are the Y1 and Y2 for distillation? Any answer?
Sir, XT and D.
Not.
So the bottom and the top product.
Yes. XD and XB. What's your roll number?
So 30036.
Who is the first student?
30034.
Yeah. 36 you told, no?
Yes, sir.
Yeah. So this is basically XD and this is XB. Okay. This is XD, this is XB. I mean, we should give priority to the product purity because, that is the main concern for us. And this one we can consider feed flow rate and feed composition. Now, from this block diagram, we can also explain the distillation process like this. Suppose there is a change in feed flow rate F1. So you see, according to this block diagram, it will affect both the top composition XT and the bottom composition XP. I repeat, if there is any change in feed flow rate, say F1, according to this block diagram, we can see it is directly affecting Y1, that is XD. It is also affecting through G21, Y2, that is XP. Fine. And similarly, we can explain for any change in F2 like feed composition also. It is also affecting the top composition Y1, that is XD, and bottom composition Y2, that is XB. Fine. That means this distillation is an interactive system. Distillation is an interactive system. If there is any change in feed flow rate, it is affecting not only the top composition, it is also affecting the bottom composition. Okay. So the system is interactive system. We'll discuss this issue later. Okay. You can just note down this term, interactive system. Okay. Now let us come to apply this transfer function concept for multi-input, multi-output system to an example, that is jacketed CSTR. In fact, we have considered this example system before. To basically convert the model in terms of deviation variables. You draw this schematic diagram. We are currently discussing the application of the multi-input, multi-output transfer function development. We would like to develop the MIMO transfer function. So one exothermic reaction occurs here, that is A to B. And we are assuming that the volume of the liquid in the tank or in the reactor constant. That is constant. Now we have seen before for this example system, we have a nonlinear model. And we have linearized that model and represented in terms of deviation variables. You can recall that model. This is the model. Okay. We have linearized that model. And in fact, there are two nonlinear terms. CA into exponential of minus E by RT, you can recall easily. And we got this model equation. So you see what we will do in the next step, we will represent these coefficients by a different notation. Okay, like this one we will represent by coefficient. This coefficient will represent by notation in terms of small a. This is also will represent by a notation. Here you put here 1/3 bracket. Okay, I missed it. Here 1/3 bracket you put. And this is one coefficient. Like this way, we can simplify this model. But here you see we have considered this capital Q equal to UA T minus TC. Okay. So what is AT? What is capital A T?
Area of heat transfer.
So what is that basically? I mean, do you have any expression for AT for this example?
So it will be the wall area.
Tell that. What is that expression I'm asking?
So 2 pi r into height.
That's it. Anyone can correct it or?
So 2 pi r into height plus pi r square.
Yes. Yes. What's your roll number?
19CH 30034.
Yes. So area is wall area you told, no? That means the side pi r square, 2 pi r into h, and this bottom section also. Okay, which is plus pi r square. So this wall 2 pi r into h, and this bottom square section, that is pi r square. Okay, now you see, as I told, we are representing the coefficients of input and output variables by a different notation, that is small a. We are now simplifying the model by representing the coefficients in terms of small a as well as small b for output and input respectively. Can you write now this model in terms of in matrix form? Write it. Write this model in matrix form. The next step is to write the model in matrix form, and you do it. You do it and let me know what form of matrix form you are getting. Anyone got the matrix form?
C inverse A of S, and like if row, a column matrix of
I think if you write in this form, you can get easily. Is this fine? And as I mentioned, you see here also input variables are in terms of deviation variables. Okay. Now in the next step, we need to take the Laplace transform. And I'm giving you directly the expressions. As I mentioned, for the general transfer function for MIMO system, you need to take the Laplace transform. And then you have to solve in terms of y1 and y2, here in terms of CA and T. Then after rearrangement, you will get these final expressions. I repeat, you have the model equations in the standard format. Take the Laplace transform and solve the two equations for CA and T, y1 and y2. After rearrangement, finally you will get these expressions. I am here directly giving you the final expressions. So how many transfer functions are there? Anyone can tell? How many transfer functions are involved in this process? You can give the answer from these two equations, or else you can give the answer from the concept of nomenclature of capital G. Suffix of G basically includes the input and output.
6.
6.
Yeah, 6. Correct. So which suffix should be 3? First or second suffix of G?
Second.
Correct. What's your roll number?
30018.
Second suffix.
Sir, can you scroll up?
Yeah. There are 2 outputs and there are 3 inputs. So total 6 transfer functions. G11, G12, G13 and G21, G22, G23. Can I proceed?
Yes, sir.
Yeah. You see this is a transfer function and this is in matrix form. There is no difficulty to understand this. If you have finished this one, you can develop the block diagram. If you have finished this matrix form, noting this matrix form, you proceed to develop the block diagram. It should be a little different block diagram than the memo system we discussed before. Proceed to develop the block diagram for this CSTR example. Three FP07. Are you there? 19 CH 3 FP07. Yasni Jain. 3PE01 Padmasri. 3PE01 Padmasri. 10074 Gaurav Jha is there. 10074 Gaurav Jha. 30038 PT Chandrakant. 30038. Are you there?
Yes, sir.
Yeah. What is the significance of capital G suffix 23? Z23. What do you understand by this nomenclature? G23. Any answer?
I'm not sure, sir, actually.
You try. It's okay.
Yes, sir.
You just tell me what is the first suffix, what is the second suffix. Try, there may be mistake, no problem. You do not want to give the answer, okay? You see, this is the block diagram. Anyone got this?
Yes, sir.
Good. If you follow the nomenclature, if you understand the nomenclature, then there is no difficulty to understand. Anyway, I repeat again. G11 indicates, first suffix indicates the output. 1 means this is the first one. And second suffix indicates the input. So first input we are considering CI. Okay, you may consider different, like TI you can consider first input, no problem. Okay, then accordingly you have to change these nomenclatures also in the model equation. And G21, first suffix indicates the output, that means T, that is second output, and second suffix indicates the first input, that is CAI. So you see CI and T, they are also connected through GT1. So like this way we made this block diagram. Okay. Yeah, anyone has any question on this? Otherwise we will move to our next topic. So I think you all understood. Okay, good. There is no difficulty at all. So our next topic is poles and zeros of transfer function. Our next topic is poles and zeros of transfer function. We are gradually entering into the stability analysis. Okay. We are gradually entering into the stability analysis. So before that, we need to know the poles and zeros of a transfer function. One thing I want to mention here, schematic control configuration block diagram do not mix up to each other. I mean, sometimes I'm asking to develop the control configuration, students are drawing the block diagram. Be cautious. Schematic diagram is basically the diagram of a process. Control configuration we have discussed before, that is the configuration which includes the sensor, controller, final control element, etc. And block diagram you understood. It is in Laplace domain and I have just shown block diagram. Okay, you remember these three because students are usually doing the mistake. Okay, like this one you see it is the process and it is given in Laplace domain. So in some sense you can tell this is a block diagram. Okay, this is a process in Laplace domain and transfer function we have defined before, output by input in Laplace domain. And now we will consider this transfer function as the ratio of two polynomials. We'll consider the transfer function is basically the ratio of two polynomials. One is in the numerator and we are denoting by capital Q. Another polynomial is in the denominator. We are representing by capital P. Okay. So transfer function is basically a ratio of two polynomials. Now you see the zeros of the transfer function of a system. I think you know this concept. If we consider QS equal to 0 and you find the roots, those roots are called zeros of the transfer function or system. Just consider QS equal to 0, find the roots, and those roots are called zeros of the transfer function or zeros of the system. Similarly, you come to consider PS equal to 0 and the corresponding roots of the polynomial are called poles of the transfer function or poles of the system. Similarly, if we consider PS equal to 0, the corresponding roots are called poles of the transfer function or poles of the system. Now let us take one example to discuss this theory. So we have a transfer function GS, which is K divided by S plus A. Now if we represent this transfer function GS as the ratio of two polynomials Q by P, so there is no pole at all. There is no root for the numerator polynomial because that is a constant term, that is not the function of Laplace domain S. So accordingly there is no 0. And if we consider PS equal to 0, we get S equal to minus A. That means we have a single pole and that is minus A. Similarly, you see we have taken another example. So we have a single 0, that is 1. And we have 2 poles, 1 and 2. In the second example, we have a single 0 is equal to 1. And we have 2 poles. One is 1, another one is 2. Now based on this, we can comment, you see, at the zeros of a system, transfer function becomes 0. And at the poles of a system, transfer function becomes infinity. In this example, if we just substitute s equal to 1, no, we'll get this gs equal to 0. That means transfer function becomes 0. It is written here. Similarly, if we just substitute here s equal to 1 or maybe 2, this gs becomes infinity. And that is written here. Okay. At the zeros, transfer function becomes 0, and at the poles, transfer function becomes infinity. Yeah, I think we do not have time to go to the next topic. So, any question? If you do not have any question, we will stop here. Thank you, students.
Thank you, sir.
Thank you, sir.